We had a brief look at how to draw up our trig graphs last year. Of course, that was in degrees, and really we only looked at the most basic of the curves. So let's just look at now how we can do any type of trig curve, and of course we want to do it in radians as well. So I'll go to the sine curve first of all. So if I'm doing the sine curve, you remember the sine curve has an amplitude of 1, the basic one. So I'll mark in 1 and minus 1 on the y-axis. And I mark off every 90 degrees, or now pi on 2 radians. Mind you, I only label every pi. And then I just basically plot those boundary points. So when is it 0? When is it at the amplitude? And if you remember, the sine curve starts at the origin. And then it goes up to 1, and then down, and it follows that nice little pattern. Now, of course, this is not like back when you were in, well, even before you went to school, and your parents gave you a dot-to-dot book, and you drew zigzaggy lines, and everything had to be joined by a straight line. We draw a nice, smooth curve. There we go. So there's y equals sine x. So that's the basic one. So the important things we need to know, the domain is all real x. There's no breaks in that curve whatsoever. The range, as I said, goes from minus 1 to 1. Odd or even? Odd, yes. It's got that rotational symmetry. So that can be useful when we're working out things, because we know if it's odd, then function, which way does it go? Function negative x is equal to, yeah, so we know therefore that the sine of negative x will equal the negative of sine x. So that can be useful. Okay, so to generalise it, there's some important things that we have. The amplitude, of course, is how high it goes up and down. And the period is how long it takes until the curve gets back to that same point, but heading in the same direction. So don't look at the x-intercepts and think, oh, it only takes pi to get back, because at pi it's going down, but at 2 pi it's going up. It actually takes 2 pi until it's back and heading in the same direction. So if I was to generalise it, a sine bx plus c. The period will always be 2 pi divided by the coefficient of x. And that goes back to our graphing idea. And if we said function constant times x, it pushed the curve in by a factor of k. So in this case, it'll be 2 pi divided by b. The amplitude will just end up being the coefficient of the trig function. There's another thing I like to work out. I mean, it's not a technical thing, but it's just so I know where to mark off my points. Because I know there's 4 key points in any period. And that's where I'm going to plot my boundary values. So whatever the period is, I'll divide that by 4, and that's where I'll mark off on my x-axis. And of course, if there is a shift happening, remember the shift is not c, but it's c divided by b. Because the shift, it has to be factorised. It has to be grouped with the x. So it's actually c divided by b if there is a shift happening. Okay, so let's do this one. 5 sine 9x minus pi on 2. All sorts of things happening here. So the period would be 2 pi on 9. So amplitude 5. I'll mark off my divisions every pi on 18. If I'm only drawing one sine curve and nothing else, I can pretty much draw the same curve for every function and just adjust the scale accordingly. So if you've got a math aid, you just go whack it down, draw the curve, and then mark in the points at the appropriate values. And this one has got a shift. It'll be pi on 18 to the right. It's moved to the right. And remember, if you're unsure, just say to yourself, what would make this equal to 0? So what would make 9x minus pi on 2 equal to 0? Well, if you sub pi on 18 in, that would make it equal to 0. All right, let's draw up our axes. Amplitude's 5, so this time I'll just mark it at 5 and minus 5. And The divisions are pi on 18, but there is a shift pi on 18 to the right. Oh, that was fortunate. I can still keep those divisions every pi on 18. If the shift was, say, let's pick another one. Say it was pi on 6, then I would have to have a marker at pi on 6 and then mark off every pi on 18 before and after that. But fortunately, this one worked out nicely. All right. My basic sine curve would start at the origin, but we've shifted pi on 18 to the right. So I will start at pi on 18. And then I know the pattern of my sine curve is I'll go up and then we'll go down and so on. And then I'll just draw in my sine curve. Now, if they ask you to draw it for a specific domain, say this question had said, draw for the domain minus pi on 9 to 2 pi on 9. This graph would be wrong because I've extended past the endpoint. Mind you, you have to in PowerPoint to get the nice curve, because if I just stop there, it would go straight. So, but, you know, only do for the domain. If they haven't specified a domain, well, terrific. Just make sure you do at least one period when you draw it. Okay, let's have a look at cosine. And you may remember cosine and sine are basically the same curve. It's just the cosine curve has been shifted 90 degrees or pi on 2 radians. So these sorts of things are going to be the same. The period is still going to be 2 pi on b. The amplitude is still going to be a. I'll still mark off my divisions every period on 4. And of course we could have some shifting happening as well. So let's draw, hey, look at this one. Minus 4 cos x on 8 plus pi, and all of that plus 2. I might have got a little carried away. You probably wouldn't get every possible shifting thing happening, but I just said, what the heck, let's do it, eh? So our period will be 2 pi divided by the coefficient of x, which in this case is 1/8. So we end up with 16 pi. The amplitude is still 4, even though it says negative 4. Remember, amplitude is a measurement. So we always give a positive value. So amplitude is 4. I will mark off my divisions every 4 pi. And this one is shifted 8 pi to the left because, again, to make that equal to 0, I'd have to sub in negative 8 pi. And we're also going 2 up. Okay, let's mark off my divisions. I'll mark off every 4 pi. Oh, but I've shifted 8 pi to the left. Oh, that was lucky. 8 pi is a multiple of 4 pi. Now, because this one is shifting up 2, I'm just going to draw in a horizontal line. It's actually dotted. I don't know if you can see it from where you are, but that is actually dotted. Just so I know where to plot the axis of the curve. And the amplitude we said was 4, so 4 up from that axis would be 6. 4 down would be negative 2. And let's mark off our horizontal axis, as I say, going to mark them off every 4 pi. Now let's think about our cosine curve. Cosine normally starts up at the peak, up at the amplitude. But this one is shifted 8 pi to the left, so I'll move to negative 8 pi, but it's also upside down. That's what the negative out the front means. So I'll now start, instead of being at the top, I'll start at the bottom. So the first point I'm going to plot is down here at negative 8 pi, negative 2. Then the cosine curve will go up to the axis, and then I'll just keep going in that pattern, like so. And there's our cosine curve. Now, that's not the basic cosine curve, but imagine the basic one, odd or even. Yeah, that one's even because it would have reflectional symmetry. So that means we can use the feature of even functions when we're playing with cosine. Function negative x will equal function x. So cosine negative x will equal the cosine of x. All right, we can't leave tangent out, it'll get lonely. So let's have a look at a tan curve. So to generalise it, a tan bx plus c. The period is different for this one. If if you remember back to our basic tan curve, it repeats every 180 degrees, or pi radians. So this one, instead of being 2 pi divided by b, it'll be pi divided by b for the period. I haven't worried about amplitude, even though I've put an a out the front there, but when you're talking about tan curves, amplitude's meaningless. It goes down to minus infinity, all the way up to infinity. It doesn't have an amplitude. And the divisions, this time it'll be the period divided by 2. Because the period is halved, then the number of divisions I need is also halved. So it's just period divided by 2 rather than period divided by 4. And of course we could have some shift happening as well. All right, let's draw a tan curve. Wow! We're going to draw y equals e tan pi x minus 2 pi. Okay. So the period will be pi divided by pi. Oh, just 1. The divisions I'll then mark off every half. And it's shifted 2 to the right. Oh, that's lucky. That's a multiple of the divisions, so I don't have to worry about that. All right, let's draw it in. Mark off my divisions. I don't have to worry about amplitude. So really, the fact that I put e out the front is irrelevant. Because if I don't put a scale on my y-axis, it doesn't matter. I can still just draw the same tan curve. All right, tan. Tan normally starts at the origin. Okay? But this one is shifted 2 to the right. So I'll start over there at 2. Now the tan curve, it alternates x-intercept, asymptote, x-intercept, asymptote. So let's put that pattern in. There's an asymptote. Go back the other way, asymptote, x-intercept, asymptote, x-intercept. And now we just have to draw in our shape. Remember, when you're drawing a tan curve, it's not a cubic. So when it comes through the axis, it is a point of inflection, but it's not a horizontal point of inflection. It comes through at 45 degrees. Okay? And so this is a bit like that. Right? So it still inflects. It's gone from concave down to concave up, but it's not a horizontal point of inflection. Those that do have the math aids, there is a tan curve on there, so that makes life a little bit easier. But of course, don't use that tan curve if you're drawing a cubic, because then it doesn't have the horizontal. Let's just complete that. There we go. Y equals E tan. Okay, 14C. Let's play with drawing up our graphs.